Okay, so today we're very happy to have Hoon Lee from Perimeter Institute for Theoretical Physics, and he'll be telling us about microscopic expansion for superconformal indices. Please, Ji.
Thank you. I'd like to start by thanking the organizers for the invitation. So I'll be talking about a work, well, two papers in the past year and a few more papers to come. And at the end, I'll list some of the ongoing pursuits. So a central question in ADS-CFT is how the degrees of freedom in string theory are organized in the dual gauge theory. And in this talk, I'll present an exact finite end formula that relates the BPS sectors of gauge theories and their string duals. And the formula I present will relate the superconformal index of a UN gauge theory and the index of bulk string brane configurations in the string dual. And it expresses a gauge theory index as a sum over branes and their open string closed excitations, where the branes that appear are dual to determinant operators in gauge theory. In the simplest settings, these branes are so-called giant graviton branes, which are supported by the RR5 form flux in the standard example in ADS5 times S5. And they wrap the time direction times some codimension 2 sphere in that example. And they're particle-like in ADS, but extend in the compact directions, which explains their name. So let's start by reviewing what holography says about partition functions and indices. A way to state ADS-CFT is as an equivalence between the partition functions of gauge and string theories. And the string partition function is often evaluated in the supergravity limit at large to coupling, lambda, as a sum over saddle geometries which satisfy the boundary condition provided by the CFT. So in many cases, there'll be, generically, there'll be sums over different black hole configurations. This sum namely includes pure ADS and many families of ADS black holes. And this is an asymptotic expression, which is valid at large n, with perturbative corrections around each saddle. So we'll study the relation between gauge and string partition function at the level of superconformal indices, which counts BPS operators up to signs. So I'll denote the superconformal index as a regular z instead of curly z. And indeed, in recent years, there have been many fruitful developments exploring the connection between superconformal index indices of gauge theories and supersymmetric black holes and gravity duals. And you can see works by these authors and more. So these works demonstrate that holographic field theories indeed contain the precise degrees of freedom to account for degeneracies of higher dimensional black holes, which not necessarily relying on the traditional techniques of the Carnot formula, but rather either it's higher dimensional variance or finding new saddles in the gauge integral of the index. In gauge theory, the superconformal index captures the BPS sector of the full Hilbert space, which is protected by superconformal symmetry. And sectors which are not BPS carry an equal number of bosons and fermions, which cancel due to -1 to the f. So BPS states and operators are annihilated by Q and Q dagger, which are Poincare and conformal supercharges. So the factor, which the exponential factor, evaluates to 1. Well, here we'll simply get a number for the number of BPS states, but it's really helpful to refine the index so that we can get more information by organizing the Hilbert space into representations that transform under the global symmetry charges CA, which commute with Q and Q dagger. So these variables are called fugacities in the literature, and they're related to chemical potentials. And the coefficient of fugacities in the index gives the degeneracy of BPS states with corresponding charge numbers up to signs. And perhaps the most important thing about the index is that it's topological. So since we can deform the CFT to a free theory and compute the index there, the index is much more tractable than a partition function. That's the merit of studying the index.
So, which geometries do you have in mind? Anything that preserves SUSY? Any amount of SUSY?
I haven't talked about any geometries until now.
Right.
I've talked about the index from the gauge theory perspective. So,
No, but I mean the wall volume geometry for the gauge theory itself.
so you mean the dual? Sorry.
No, the gauge theory itself is top. You're putting the gauge theory on something.
Oh, that's right.
Yeah.
Sorry, I didn't specify this, but I'm putting the gauge theory on S1 cross S3. So
Okay.
for the talk, I'll limit myself to four-dimensional gauge theories and place the index on, compute the index on S1 cross S3. Sorry, that was an important point that I forgot to put in the slide. So in the talk, I want to provide a microscopic perspective on the connection between superconformal indices and black holes. Rather than a direct saddle approach, which was pursued in the cited examples. To this end, I present an expansion for the superconformal index that makes manifest the microscopic ingredients in the bulk, namely the string brane configurations. So the terms that we proposed in our paper last year in the expansion admit natural interpretations in string theory rather than in supergravity as giant graviton branes and their string excitations. So the claim is that the finite and index of the gauge theory, which you can see on the left-hand side, is a sum over various numbers of branes, where the index under K denotes the types of branes that contribute, and K is the number of that type of brane that contributes. Such a formula seems to be generally applicable, at least in four-dimensional gauge theories. There's actually some good evidence and actually a mathematical theorem which guarantees the existence of such an expansion for any UN gauge theory with adjoint matter. But the physical interpretation of the terms in the sum as giant graviton branes and their string excitations is what I want to present in the talk.
And the KIs are what?
So the KIs denote numbers of a certain kind of brane that contribute to the sum. So there are S types of branes. I'm writing a general formula, but this formula is theory specific. So for some sector of a gauge theory, say I restrict to the half BPS sector in n equals 2 for superangles. S is 1. There's just one type of giant graviton that contributes. And there are K numbers of coincident giant gravitons which contribute in the sum.
And the N is there because D branes typically have a cost of order N?
That's right, yeah.
Okay.
So each of these terms are suppressed by e to the minus sum of k's times n. There are exponential contributions in the spectrum. Okay. So Zn is the index of a UN gauge theory, or via ADS-CFT, the index of its string theory dual on a background with n units of RR flux. The closed string spectrum, Z infinity, has an interpretation in the supergravity regime as the index of Kaluza-Klein modes. And in fact, Z infinity is simply the Zn with n taken to infinity, which is readily calculable. And there are S types of branes. The terms in the sum are stacks of Ki numbers of branes of the ith type, where each brane has charges of order n. And the brane index, Z hat, enumerates the allowed open string excitations on the brane stack labeled by the list of Ks. So the surprise is that the expansion appears to be convergent at finite n when all fugacities take values in the unit disk. So, and there are very explicit examples of this that I'll show later. So there are reasons to believe that the formula is best interpreted in the stringy regime where lambda goes to 0, though the collective degeneracies of string and brane configurations should agree with those from supergravity saddles at large lambda. And they agree because the indices are protected under changes in lambda.
What is lambda?
Lambda is tuff coupling.
Okay.
And namely, the fact, so the theorem I referred to earlier was referred to in a paper by Samir Murthy this past April. And the theorem by Borden and Okunkov, which Samir cites, guarantees an expansion of this sort for any UN gauge theory index with adjoint matter only. But the formula is more general, and there are examples of this formula for cases with, say, fundamental and anti-fundamental matter.
So this is so far a calculation in the gauge theory.
Everything can be constructed in gauge theory.
Right, but when the words you put around Z infinity was a contribution from the Kaluza-Klein modes, and that sounds like a bulk
That's right.
statement.
They have natural interpretations in the bulk.
So is this corresponding statement in the gauge theory that it's some kind of contribution of single trace operators?
Yes, the multi-trace operators. Products of single trace operators.
So I'm to interpret Z infinity as contributions from multi-trace operators, and then everything after that is some contribution of determinant operators?
That's right.
Okay. But that's some kind of overcounting, right? Because at finite n,
that's
can
right.
represent one in terms of the other.
That's right. But so what's fascinating, which happens in the bulk side, which I'm going to call the right-hand side the bulk side, because it seems to have the most natural interpretation in the bulk. What's fascinating is that there are drastic cancellations on the right-hand side, which conspire to collapse into the finite n gauge theory index. So naively, the string dual side seems to have many more states, but they sort of miraculously cancel, and one can empirically demonstrate such a cancellation in various examples. So instead of posing a string exclusion principle, where one says, well, we can trust supergravity until of order n, and then there we should cut off the supergravity states and consider, say, giant gravitons instead. Here, you're really counting everything that's in there, that one might suppose is there in the bulk string dual, but the contributions that you get at the end are canceling each other out in a way that reduces the final result to the finite n index. So we can compare our formula to the sum over geometries. And for concreteness, we'll discuss the canonical example of UN n equals to 4 superang mills and type 2b strings on 85 times S5. We expect to see the following bulk states in the spectrum. So at charges of order at charges of order 1, perturbative excitations of ADS5 times S5 corresponding to supergravitons and strings. And at charges of order n, you expect to see non-perturbative excitations such as d-branes. And at charges of order n squared, one expects to see fully back-reacted, highly excited geometries such as BPS black holes or bubbling geometries. The statement of the giant graviton expansion implies that a careful counting of the order 1 and order n contributions in string theory only is sufficient to reproduce the degeneracy of supergravity saddles at order n squared.
Is this some kind of ADS5 version of the fairy tale expansion?
Well, here we're not summing over geometries, but instead over different numbers of branes and
Well, but that was some sort of result that said that only looking at the sort of polar terms in the elliptic genus, you could infer the rest of the elliptic genus. Just looking at its behavior at levels less than of order of the central charge. So this sounds like a very similar statement.
perhaps, although I'm not sure whether the objects that they're summing over in the fairy tale story are have a brain-like interpretation. But what you say is correct, but I'm not sure if the as far as I'm aware, they're summing over saddles in ADS3. That happens to be an exact formula in the three-dimensional case, but it seems that in higher dimensions, there are contributions from branes which kick in at every interval of n. Seems to be sufficient to produce the order n squared degeneracies.
Okay.
Black holes, so just make sure I understand. So the black hole states are different, would be different string theory backgrounds that are all being captured by, if you want to say, perturbative plus branes, plus d branes in around affix background. Can we go back to the previous slide for a second? I just want to make sure I understand what applies to what. So you want to say perturbative around ADS5 plus d branes is capturing black holes potentially.
Yes, I understood what research is.
So what I'm saying is that non-perturbative excitations, which are suppressed like e to the minus n, are essentially giving you the results that you would get by summing over geometries which could get at e to the minus n squared.
So you're saying the sum of the geometries is captured by contributions around a given background.
The vacuum dimension,
for example. Yeah.
I'm still a little bit puzzled. So as to what this last sentence is what's confusing me. So are you saying if you extrapolate the counting that you do in the first two bullet points to the regime where the last bullet point applies, that the expressions that you wrote down extrapolate to correct expressions in energies of order n squared? What?
Yes. So
what do you mean?
The gauge theory index contains those supergravity saddles.
Right.
You agree? So if the terms on the right-hand side reproduces the gauge theory index exactly, then it's capturing the sum over saddles. But how it does so is certainly unclear. That's an open direction. There hasn't been a reformulation of of the order 1 and order n contributions into saddles. There certainly hasn't been.
But if you go back to your
Because
formula.
if I go to, if I were to calculate in regimes of order n squared, right, the previous people's results say there is some 1/16 BPS black hole geometry
Yeah.
whose free energy and entropy compute some, large spectrum of BPS states. But it's not by virtue of counting individual states. It's just that there's an entropy. It's like every other supergravity black hole, right?
Yeah.
The supergravity is not counting individual microstates. It's giving you some entropy, which is the typical number of microstates at some set of charges. So
But that can't be mapped from the.
so is it more like there's some statement that in the weak coupling gauge theory, I can do this calculation and count all of these determinant operators and so on, where there's like no gravity around at all, because it's a weakly coupled gauge theory. Even though I'm at energies of order n squared, I can make the coupling weak enough that I can do a perturbative analysis because it's an index.
But it's the index, so.
Yeah, the index doesn't care. So so is this more in that spirit where you say, I'm going to do this counting and verify this formula in some extremely weakly coupled regime, and then I know it has to apply also in the strongly coupled theory where it's a gravity calculation?
Yes, that's the extrapolation.
Okay.
So yeah, as far as I'm aware, the best interpretation of the order 1 and order n ingredients are in the tensionless string theory limit of lambda going to 0. And that is where exactly that's exactly where I'll construct the indices describing determinant modifications. That's where I'll present the construction of the string brane configuration index. So let's now return to the question of how the bulk degrees of freedom are organized in the dual gauge theory. I claim that the branes that appear in the formula are dual to determinant operators of BPS fields in gauge theory. And they may look like a determinant of a scalar, determinant of a field strength component, or a determinant of a gauging of bilinear, say, where the precise set of determinants that contribute depend on the theory, of course. And open string excitations on the branes are given by modifications of determinant operators. So if you have a explicit formula for a determinant, we'll do a counting, we'll solve a counting problem where one replaces one of the x's by some set of other fields in the theory, in free field theory. So the physics on giant graviton branes is captured by the effective theory of modifications of determinant operators in a gauge theory. And there are subtleties in computing the spectrum of these modifications due to an analytic continuation that I may or may not have some time to describe. So in practice, we use the holographic relation between branes and determinants to compute the indices of string brane configurations. And in situations where ADS-CFT is well established, our brane indices agree with direct bulk computations that count modes on branes wrapped on supersymmetric cycles in the pro-brane approximation. And you can refer to the parallel work by Imamura for that counting. So let's now derive the string and brane terms in the expansion. To do so requires some knowledge of how to compute superconformal indices. As mentioned before, the index can be computed in the free theory, where the couplings are turned off. And in a free theory, the computation becomes a combinatorial problem of counting the ways in which different letters, which I call Li, And here, I'll restrict to adjoint letters, although the construction is more general. And these LIs correspond to BPS fields and their derivatives. And so the computation becomes a combinatorial problem of counting the ways in which different letters corresponding to BPS fields and their derivatives can be combined into gauge invariant operators. A standard trick is to first count all the single letters, which one collects into a function of y, called the single letter index. Then one applies an operation called the plethistic exponential, which automatically counts all the ways in which LIs are combined into polynomials. Well, now we have to impose gauge invariance on these polynomials. And to do so, we multiply f, which only contains adjoint letters, by the un adjoint character, and we integrate over un. So this is the superconformal index of a UN gauge theory. The extra factor in the measure is the van der Waals determinant for UN, and the integral extracts the singlet sector of the integrand onto the gauge group UN. Okay, so let's now review the derivation of the prefactor z infinity from closed strings in this formula. This is a well-known result. So this contribution is given by the gauge theory index evaluated at n equals to infinity, which people have checked agrees with Kaluza-Klein modes in the bulk. The UN index can be computed exactly in the limit where n is taken to infinity. And it's a standard result that the gauge integral becomes Gaussian and evaluates this infinite product. So this index counts up to signs all multi-trace operators that belong to a given BPS sector. For example, in the half BPS sector of n equals to 4 superang mils, the single letter index is f of x. There's only the adjoint scalar x. And the infinite n index counts all operators of this form, which is a product of trace of x to some power. When considering brane contribution shortly, it'll also be important that the infinite n formula is readily generalized for theories with anti-fundamental matter, with the corresponding fundamental and anti-fundamental indices, v and v bar. So now let's derive the brane and open string terms that show up on the right-hand side of this formula. And it'll be necessary to assume that n is large for the derivation. The justification of the formula at finite n comes from direct computational checks. And for simplicity, I'll discuss the derivation in sectors where only a single type of brane contributes, although the full derivation covers more general situations. And such an expansion, where only a single type of brane contributes, appears in the half BPS sector of n equals to 4 superang mils. So in n equals to 4 superang mils, determinants of complex scalars have dimension n and are dual to the 3 giant graviton branes that wrap the corresponding cycle. And we'll reuse the relation between determinant operators and giant graviton to holographically construct the indices of bulk string brane configurations. Again, for an example like this, where the holographic dual is well known, one can use the brane action to directly count modes on the brane. And that was done by Imamura in a parallel work, and the resulting indices agree. We start with a single determinant of fugacity x to the n. This determinant can be modified by replacing a finite number of the above x's by strings of letters in the theory. So for example, we can replace an x with a string of letters, L1, L2, L1, to get an object like this. And to count all of these modifications is what we want to do. So So there are some redundancies in counting such modifications though. So an example is a replacement of the form x going to something proportional to itself, where antisymmetry allows one to write trace of w, write this modification as trace of w times the determinant of x. And the traces we're already counting, the traces are already accounted for in the z infinity factor, which counts multi-traces. So we want to get rid of these redundancies, but include them back later in the form of z infinity. For now, let's focus on the non-redundant part, which corresponds to open strings. And a helpful reformulation of the problem is to write the determinant as an integral over auxiliary fundamental and anti-fundamental fermions. And introducing these fermions adds boundaries to the Riven diagrams, which helps understand why determinants might correspond to d-brane insertions. So in terms of the fermion integral, the determinant modifications correspond to operator insertions of that form, where an open string excitation generically looks like a series of letters sandwiched between fundamental and anti-fundamental fermion. The redundancy of extra closed string mentioned above becomes a Ward identity for the fermions. And we can implement these Ward identities by introducing bosonic antifields U and U bar, as well as a BRST differential delta, which acts in this way. So it acts trivially on all the on X and the fermions, but it only acts non-trivially on U. So we're interested in operators in this BRST cohomology with ghost number 0. And the action of delta was designed so that redundancies due to replacements of the form x going to xw or x going to wx becomes delta exact. So these were the closed string redundancies that we wanted to remove. So we wanted to become delta exact. So these letters are counted, so the fundamental and anti-fundamental letters, which we call V and V bar, are counted, are given in this form. And sigma denotes a fugacity for an extra U1 symmetry, which only acts on these auxiliary variables. It'll drop out of calculations now, but sigma will be useful soon. It'll become an emergent gauge parameter in the UK integral. So now let's look back at the large N Gaussian index formula with these anti-fundamentals. So this is the large N index of a UN gauge theory in the presence of determinants, for which V and V bar we just stated. The infinite prefactor is the redundant closed string spectrum Z infinity, which we ignore for now. So this is the Z infinity factor. The large N formula suggests that the effective single letter index governing the determinant fluctuations is this object. We had to introduce an extra fermion, extra factor of 1 to cancel a fermion zero mode. So that's one catch in the derivation, but so it's a heuristic derivation which works. So let's apply this relation to the hat BPS examples where the single letter index is f equals to x. Plugging in f equals to x in the formula for z hat gives you f hat equals to x inverse So this is the single letter index of the world volume theory on the hat BPS giant graviton. And this makes sense. So here is the only non-trivial operator is x. So any modification of determinant x would correspond to replacing a single letter x by the identity operator I. And that would take away a single power of fugacity x. So it makes sense that the excitations are described by fugacity x inverse. So now it's straightforward to consider the modifications of k determinants using the fermion prescription with k flavors of fermions. And interpreting the extra variables sigma A as UK gauge fugacities, modifications of k determinants of the same type are described by this index. Now, this is an effective UK world volume theory on giant graviton branes dual to determinant x to the k. And to get the hat BPS index, we simply set f hat equals to x inverse. And due to the inverse power, a careful counter prescription or analytic continuation is required to compute the world volume index. More generally, we can repeat the exercise or modification of a product of determinants and find the index of the UK quiver gauge theory on branes dual to determinants. And these are the superconformal indices that count bulk string brane configurations. And so there will be now adjunct strings between coincident branes of the same type, as well as bifundamental strings on the intersection of branes wrapping different cycles. And one can derive precisely their single letter indices corresponding to these adjunct and bifundamental strings with our prescription. So let's put back in the closed sector and the bare fugacity x to the k n for k determinants. The index of k giant gravitons and their open closed string excitations is given by the product of those factors, where again x to the k times n is the bare fugacity of the determinant. Z infinity is a closed string spectrum, and Z hat k are analytically continued open string excitations on k coincident giant gravitons.
So where was the analytic continuation needed? I missed that.
I'll provide an explicit example which shows you where the analytic continuation comes in. So what we did was we took a large N determinant, we solved the counting problem of modifications of gauge invariant modification of this determinant by determining the single letter index corresponding to the open string excitations. But that single letter index came in the form of an X inverse. So when one is counting the spectrum, when one is evaluating the index, for example, one takes a power series in X rather than X inverse. So if your single letter index is X inverse, one has to compute the result and analytically continue that result from X outside the unit disk to inside the unit disk to expand it in X. So this part is crucial in the construction and gives rise to some intrinsic implications that I'll discuss at the end.
Okay.
So the brane expansion for the UN gauge theory index is simply a sum of the above ingredients over all numbers of branes.
So can we say a little more explicitly what Z hat K is purely from gauge theory?
Yes.
Is that reference to branes?
Yes. So the hat K is the UK gauge theory describing modifications of a large N determinant sitting inside a UN gauge theory.
So it's operators that involve some number of epsilon that is controlled by k. Is it
Epsilon's meaning,
Levi-Civita symbols? Like,
yeah, yes. But what z hat is an analytically continued quantity of the result that you get from counting modifications of the object epsilon times n numbers of x's. So you solve the counting problem and then you analytically continue your result.
is z hat k a meaningful partition function of the gauge theory on its own? Is it an observable of the 4D theory?
No, it's not. It's an object. It's an object. It's a combinatorial object that you can construct. Its interpretation is the index of UK quiver gauge theory living on the world volume of the giant gravitons in the bulk. So, I mean, if you want, you can purely take it as a relation between a non-trivial relation between gauge theory indices. So in simple situations, we can write down the giant graviton expansion explicitly. So in the hat BPS sector of n equals to 4 superrang mils, on the left-hand side is a well-known formula describing the counting problem of a product of traces with trace relations at finite n. On the right-hand side is a sum over terms which we interpret as coming from k numbers of giant gravitons and their open string excitations. Open string excitations carry the fugacity x inverse rather than x. And this x needs to be analytically continued from outside the unit disk to inside the unit disk. That's the analytic continuation step. So one can also write down a similar formula in the quarter BPS sector. So in general, the UK quiver gauge integrals cannot be evaluated in closed forms, like the nice examples I showed in the previous slide. And in a recent work, I provided a prescription to determine and evaluate the integration cycles for indices of bulk string brane configurations, which are the z hats. And these examples include string duals of n equals to 1 and n equals to 2 gauge theories, and various BPS sectors of UN n equals to 4 superrang mils. So what I find most exciting about the brane expansion is that it gives us a glimpse of what string theory could look like at finite integer values of n. So I'd like to make two remarks regarding this point. So, for example, taking the formula seriously, we can begin to ask questions such as which string brane configurations form a basis of a bulk BPS Hilbert space. So the brane expansion poses some sharp puzzles regarding the bulk BPS Hilbert space, which I may discuss later if time allows. So the second point that I'd like to make is that if the string dual of the UN gauge theory admits a supergravity regime with BPS black holes, the formula provides an understanding of the precise set of string brane configurations that make up the black holes in the large n limit. If one were to understand which set of determinants contribute in the formula. So how exactly the degeneracy of string brane configurations assemble to produce the degeneracies of highly excited supergravity solution is an important open problem. And I think there are many fertile avenues of research along these lines and hope that we can explore them in the near future. Thank you. I do do have some extra slides on the first remark, but maybe I can take some questions first.
No, you started, I think, 10 minutes late.
Oh, that's right.
So in principle, you have another 10 minutes if you want.
Yeah, if there are questions, I can take them.
In the beginning, you mentioned how the fugacities are limited to the unit disk. Could you give a physical interpretation, and also is it obvious from the complex analysis you did at some point why they have to lie on the unit disk for convergence?
So well, we understand the index as a counting function of bosons minus fermions in a certain BPS sector with a certain label of charges. And when we understand it in that way, we encode it into a generating function, which is a series in X with some coefficients, right? So that's why X has to sit inside the unit disk, because we interpret it because of the physical interpretation. But if one were to be able to sum all the contributions, it's possible to analytically continue that index result or the partition function result outside the regime of fugacities that where one first considered it. And the brane indices were originally defined outside the unit disk, and the analytic continuation problem one has to solve is to continue the result from outside the unit disk to back inside the unit disk, and interpret as physical objects when expanded in X rather than X inverse. Okay, well. So I have some additional notes on the bulk BPS Hilbert space. So consider at finite n, the half BPS sector of n equals to 4 superang mils in type 2b string theory, which we described earlier. So this half BPS sector is spanned by multi-trace operators, which is a product of trace of x to some power subject to trace relations at finite n. And in this sector, there are only bosons in gauge theory. So the half BPS index is the half BPS partition function. As we showed earlier, the giant graviton expansion can be written explicitly, where stacks of D3 giants dual to determinant of x to k wrap codimension 2 circle sphere in ADS5 times S5. I think I described the ingredients, so I'll skip these comments. So the inverse power appears because half BPS open strings take away R charges from giants. So giants already, these maximal giants already have the full n unit of R charges. So the only BPS excitations that they admit are the ones that take away these R charges.
So in the bulk language, so you would say you have a bunch of giant gravitons that carry the same spin. So there's sort of some spheres, sort of K coincident spheres on the S5 that you're wrapping some D3 brane around.
Right.
And the statement is that if you try to put an open string on that thing, it has to be somehow spinning less rapidly on the S5?
Yeah, so the giant gravitons that we considered, which are the maximal giants, have R charges of order n. So they're really wrapping the maximal cycle that it can on the S5. So it's wrapping the maximal S3 in the S5. So, and the only excitations that it can admit are ones that take away the R charges.
Right. So I guess it's, right, so it's, right, so the unexcited giant graviton is, our charge is just some angular momentum on the S5. So it's
Yeah.
just spinning the most rapidly it can spin.
Yes.
You say, if I want to excite it at all, it needs to be spinning less than the maximum amount.
So it's not, so the angular momentum isn't really from mechanically spinning with angular momentum of order n. The angular momentum actually comes from
Some
from the-
interaction of the fields.
the RR flux.
Yeah.
It comes from the RR flux.
Right.
So actually, these maximal giant gravitons have no mechanical angular momentum, but they only have the angular momentum contributions from the RR flux.
Okay.
And since it's wrapping a maximal S3, any excitation needs to sort of decrease the sizes of this brane.
Okay.
That's sort of the intuition for why the inverse power appears. And so, well, when comparing the brane and gauge theory partition functions, we should analytically continue X from outside to inside the complex unit disk. So here's an important consequence of the analytic continuation. It's that z hat k acquires an overall minus sign for odd k. So this part will give an expansion with positive coefficients, but there's a k-dependent factor, minus 1 to the k. So in the sense, D3 giants become effective fermions, which results in effective Z2 grading when interpreted in the bulk BPS Hilbert space. And I claimed earlier that the hat BPS index is the hat BPS partition function. So it counts all the objects in the gauge theory side with positive coefficients. However, if you look at the bulk side of the formula, there are vast cancellations of coefficients, even though the gauge theory only has bosons. So what's going on?
And is this related to the fact that in the bulk geometry, these Maldacena, Lin, Lunin, so in the strong coupling region, right, where there really are honest to goodness geometries, there's an enumeration of geometries that was given by Lin, Lunin, and Maldacena.
Yeah.
And in that sort of counting, it looks like the giant gravitons are like fermions on some phase space.
Yes.
Is this exactly that same?
Yeah, it seems to be a reflection of that fact at the level of the spectrum.
Okay.
But the origin, the physical origin of the minus 1 to the k is still unclear.
Mhm.
In the physical origin in the bulk, apart from the mathematical argument of analytic continuation.
Okay.
So the result is that the coefficients of the hat BPS partition function, Zn, arise in the bulk from graded dimensions of the fog space of giant gravitons and their analytically continued excitations. Well, the above statement is actually in naive conflict with holography, which is why I mentioned that there is a sharp puzzle. If one supposes that holography means the Hilbert space, BPS Hilbert space of the boundary equals to BPS space of the bulk. If such a statement is true, they're in conflict because the right-hand side counts many more states than the left-hand side. When n takes a finite integer value, the giant graviton expansion suggests that perhaps a more useful way to view the bulk BPS Hilbert space is as some resolution of the gauge theory BPS Hilbert space, where an equivalence of partition functions can be realized without having equivalence of Hilbert spaces at finite n. So a question that's in progress is whether there is an explicit bulk mechanism for the effective -1 to the k. Okay, yeah, that's what I wanted to say. Thank you.
I didn't understand the last comment at all. I thought that part of the statement of holography was that the Hilbert space is agreed.
That is the statement of holography, yes. And that's why there's a conflict. And we know such a statement holds at large n.
Well, careful. So I would have said that one's naive intuition based on n equals infinity is that there are independent states in the Hilbert space for gases of gravitons and d-branes with gases of open strings. And at finite n, you know there has to be a relation because of trace relations. So it's that, yes, there are these states, but they're not independent of one another. So
Yeah, which seems to be reflected in the cancellations in the bulk.
well, is it a cancellation in the bulk? It's not really a cancellation. It's a statement that certain states that you thought were independent actually are not actually independent.
Yes, yeah. So in the end, this might hold true, but if one asks the question of what might be a useful way to think about the BPS Hilbert space in the bulk, well, the giant graviton expansion seems to suggest that a useful way to think about the bulk Hilbert space is as some resolution of the gauge theory Hilbert space, rather than. Do you see what I mean?
Well, so
But wouldn't you, I like Emil's interpretation better. Wouldn't you say that you're just summing over some kind of redundant set of states in the bulk?
I agree, but
I think the way I would say it is that suppose you try to wiggle you start with some state and you try to wiggle it by making some graviton perturbation in the bulk. And you find you can't make that perturbation to the system without simultaneously making some D3 brane excitation. There just is no way of exciting the system that independently wiggles the D3 branes and the gravitons, that there's like one excitation that makes little wiggles of both of them at the same time, which is just another way of saying that your naive counting of bulk degrees of freedom is too generous.
But it's, the fact that the index calculation works makes it sound like there should be a limit of the bulk string theory where the naive count was correct.
Yeah, and goes to infinity.
No, but at n goes to infinity, you don't get this.
Actually, no, yeah, that's wrong. Well, no, let's see.
n goes to infinity is just the limit where you don't consider.
You don't consider those at all. Yeah. So somehow I would have preferred if there was a limit where those degrees of freedom really were independent and it was correct to count them with signs, and then when you're away from that zero coupling region or whatever, they then cancel. But I don't see that yet. Like, in a sense, if the interpretation that you're giving is right, Emil, with, there's not independent degrees of freedom, you might have wondered why this expansion from the bulk worked at all. Like, what was the limit where it was justified?
It's probably justified if you say, I'm interested in having a giant graviton in the system, okay? And then I take n to infinity, holding the energy scale at which I'm looking at the system to be scaling with n in the appropriate way, that giant graviton stays in. In other words, it's the same thing. Like if I'm interested in black holes and I try to take n goes to infinity, then the black holes go up to infinite energy and decouple from the system. But if I say, okay, I'm interested in studying a black hole in ADS5 cross S5, I hold my energy scale fixed at some number of order n squared. And then I look at excitations around that have finite energy. And so I think, the limit in which maybe there's some sense in which you can think of these bulk gravitons and d branes as being sort of independent excitations is some limit like that, where I say, I'm interested in energies of order n in the n goes to infinity limit. And
They
then you say,
become effective.
then I'll have some open strings on the d brane, and I'll have some closed strings in the bulk. And because I've taken the large n limit, I'm in some weakly coupled supergravity where they don't talk to each other.
Yeah, okay, that makes sense.
Let's thank Ji Hoon again.
Could these be related to the